There are many ways to reduce the environmental footprint of our buildings, such as installing renewable energy technologies on buildings themselves. In Canada, the most common clean technology installed on buildings are photovoltaic panels, also called solar panels, which use the sun's energy to generate electricity without emitting greenhouse gases. Because photovoltaic systems are typically found on rooftops, the surface area that can be used to produce electricity is limited. These systems can also pose a challenge in terms of building aesthetics. Today, one of the most promising technologies to generate on-site green electricity for buildings is building integrated photovoltaics.
Good day everyone, our topic for today is all about the latest invention in the field of civil engineering, which is the Building Integrated Photovoltaic Glazing System. This system replaces the outer building envelope skin, thus serving simultaneously as both a climate screen and a power source generating electricity. Here is the table of contents in my discussion. First, the overview. The overview composes the short discussion about the Building Integrated Photovoltaic Glazing System, such as the definition and its purpose. Next is the outcome, which contains the benefits of BIPV. Lastly is the chemistry behind it, that includes the different facts and explanation on how and why it was developed. What is BIPV? Building Integrated Photovoltaic Glazing System, or BIPV, is a system which helps the building to generate their own electricity by transforming the whole building into a solar panel, and in other words, photovoltaic glazing system not only produce electricity, they also part of the building. This system replaces parts of the conventional building materials such as the roofs, windows, and facades to increase energy efficiency to meet buildings' energy demand. Windows, skylights, facade shelves can be designed to receive more daylight energy. These systems are planned during the architectural design stage and added during the initial constructional phase. In this system, a transparent photovoltaic glass acts as a structural building material. In many developed countries such as London, Brazil, South Korea, and Japan, photovoltaic glazing system has been used widely since it also contributes to developing net zero energy buildings and serve as a structural or design elements. Building integrated photovoltaic glazing system can be installed during the construction phase of a building or deployed in the course of a retrofit of an existing building when one of the envelope components needs to be replaced. The built environment allows for many ways to integrate BIPV. In general, there are three main application areas for BIPV, such as the roofs, facades, and externally integrated systems. The first application is the roof tiles. That includes the shingles, tiles, and skylights. Roof tiles. It is a way of replacing traditional roofing materials into a photovoltaic roof tiles. And photovoltaic shingles can replace common roofing shingles. It looks like ordinary roofing shingles, but they generate electricity. They were laid out and nailed to the roof using the same method as are used to lay conventional shingles. Various opportunities for innovative architectural design, which may also be aesthetically pleasing, are provided also in the photovoltaic roof tiles and shingles. Therefore, this is preferred by some architects. Next is the facades. That includes the cladding, curtain walls, and the windows. In facades, there are few options available in determining what to do with your photovoltaic in sections of the building besides the roof, which is the facades. The first one is to integrate into the walls. Perfectly vertical walls, of course, do not receive the same solar radiation the way slanted or horizontal roofs do, but they do receive some, especially if the building is located in the higher latitudes, where the winter sun comes in a low angles. The second option is to integrate the modules into the building's surrounding skin. Some buildings incorporate such a scheme for aesthetic as well as for the climate control purposes. If the panels were much like windows, capable of opening and closing, they could play a direct role in controlling the climate of the building, while at the same time having enough space to keep cool and therefore function efficiently. Lastly is the externally integrated systems that includes the balcony railings and shading systems. Solar awnings, or what we call the externally integrated systems, are advantageous in the way that they can keep the unwanted direct rays of the sun out of your eyes while absorbing them to create electricity. The angle of awnings could potentially be adjusted to best capture or block rays of the sun depending on the season, if it is summer or winter. Then, we are done in the different forms of BIPV, and let's move on the benefits of building integrated photovoltaic glazing system. One of the benefits of the BIPV is the aesthetic appearance of it because it replaces the ordinary roof's packaged and externally integrated system into more pleasing appearance, as well as it provides comforts and ensures healthy natural lighting. Additionally, it saves money in energy bills because it uses the solar energy from the sun to generate electricity in the whole building. It also helps to reduce the carbon footprint and preventing global warming since it uses renewable and sustainable energy. After discussing the benefits of building integrated photovoltaic glazing system, let's discuss also about the chemistry behind it. The main element in the photovoltaic system is the photovoltaic cells that is made up of semiconductor materials such as the silicon. Many individual cells are interconnected to form a module. These modules are strung together in a series with cables and wires to form a photovoltaic array, which we call as a photovoltaic cells in a solar panel. The sunlight shining on solar panels induces photoelectric effect, which converts sunlight into electricity. Hi there guys! I will be discussing the principle of solar cells that is based on the principle of photoelectric effect. And I'm going to show you an animation from YouTube while I am discussing it in front of you for you to understand it better. We will be discussing the principle of solar cell that is based on the principle of photoelectric effect. A solar cell gathers light from the sun and generates electricity, just as a leaf generates food for a plant. Let's find out how. The sun emits energy in the form of waves. These waves can range in length, from short ultraviolet waves through the rainbow of the visible spectrum to long infrared waves. When the sun is shining, these waves move toward the earth and hit the surface of solar cells. Anyway, let's get into the structure of one of those solar cells. They might look like one thing, but there are several layers. First is the metal plate on the back, two different types of semiconductors, a metal grid on the front, an anti-reflection coating, and a piece of glass. The first layer the light encounters is a glass. Glass is an insulator, so it's not going to conduct any noticeable electricity. It is also transparent, so most of the light just passes through. The reason it's there is to keep everything else out. Next is the anti-reflection layer. That's the layer that makes the solar cell look dark. The semiconductors underneath are a bit too shiny. If they were exposed, over 30% of the light will just reflect away. That simply won't do. So, this coating has to be transparent. It must let the light pass through. Next is the silicon. We need help from the second most abundant element on Earth, sun. The sun has to be converted to 99.999% pure silicon crystals to use in solar cells. To achieve this, the sun has to go through a complex purification process as shown. The raw silicon gets converted into a gaseous silicon compound form. This is then mixed with hydrogen to get highly purified polycrystalline silicon. These silicon ingots are reshaped and converted into very thin slices called silicon vapors. Silicon is a semiconductor material, a type of material that normally cannot conduct electricity well. But it can be made more conductive under certain conditions. The semiconductor part of the solar cell has three layers. The thin top layer contains silicon and a very tiny amount of element, such as phosphorus, that has more electrons than silicon. This gives the top layer an excess of electrons that are free to move and make the material more conductive. The top layer is also called negative type or N-type, as it favors the collection and transport of electrons. The thin bottom layer contains both silicon and an element, such as boron, that has fewer electrons than silicon. This gives the bottom layer fewer electrons that are free to move, therefore making the material less conductive for electrons. A missing electron can be described as an effective positive charge. Therefore, the bottom layer is also called positive type or P-type, as it is preferentially favors the collection and transport of these positive charges, also dubbed holes. The thicker middle layer has only slightly fewer electrons, making it marginally P-type. Thin metal lines typically made of silver are printed on the top N-type layer, and the bottom P-type layer is in contact with an aluminum plate. When light waves hit the top surface of the silicon solar cell, only light with wavelengths from a specific window of solar spectrum, 350 to 1140 nanometer, are absorbed into the middle layer of the solar cell. This range of wavelengths includes the visible spectrum. Ultraviolet wavelengths are so short, they stop at the surface, and infrared wavelengths are so long, they cannot be absorbed and pass right through the cell, or are reflected back. The light wave knocks an electron of a silicon atom, setting the electron loose and leaving an area of positive charge, a hole, where the electron used to be. The loose electron then moves towards the top and reaches the top N-type layer, which readily accepts electron. Similarly, loose holes moves towards the bottom and reaches the bottom P-type layer, which readily accepts holes. This continues as long as sunlight shines on the solar cell. Now that electrons and the holes have been separated, connecting a wire between the top and the bottom metal electrodes provides a pathway for the electrons to move towards the holes. Flow of electrons is electrical current. Solar cells produce several watts of power. This may be sufficient for running a calculator or a phone charger, but it's not sufficient for running a toaster or even an oven, for example, which use 1000 watts. So several cells, typically 32, are wired together to make a solar panel. Several solar panels are needed to generate enough electricity to power up a household. Like leaves that generates food for the plants, solar cells are a viable way to convert the sun's rays directly into electricity that we can use. Future challenges includes the improving the efficiency by which solar cells convert sunlight's electricity and make the solar energy cheaper. Of course, solar cells produce electricity only during the day, so storing the electricity efficiently for use for nighttime is another important challenge. Advancement in solar technologies presents potential to our lives if we just leave it to the sun. That is the end of our discussion about the latest innovation in the field of civil engineering. Again, I am Camille Pasion from the program of Bachelor of Science in Civil Engineering in Colegio de Muntinlupa. Thank you and God bless.